So we have to recall the following fact that if this is an inner product on a real vector space, with basis some b, then if you look at the matrix of that inner product, then let's call this matrix A. Then this matrix A will satisfy two things. Its transpose will be equal to itself. And the reason for that is if you have UV inner product, that's same as VU. This translates to this being symmetric. And moreover, it will also have the property that you write it as this symbol, but this means positive definite. And I explained positive definiteness in a few different ways. One quick way to say it is like if you have a matrix, and you can just start taking the minor matrices from the top left corner, and you increase it, and all the determinant has to be positive. If that's true, then it's called positive definite. I like this because it's simple to explain, but I don't like it because it doesn't really give you the intuition of what this actually means. The actual meaning of positive definiteness is that if you have any vector u as a column vector, then UTAU will give you a number, and that number would be bigger than 0. That's what this symbol really means. Okay? And this just means that I wanted to not say too much, but I guess I end up saying a little bit more. So, see, you can use that matrix to represent this inner product as follows. If you have U and V, let's say these are column vectors, okay? Then this is same as calculating U transpose A and V, okay? That's the relationship, okay? So when I say the representation of the inner product with respect to this basis, I really should. U under this basis, transpose A, B under this basis. It just looks bad. I mean, all I'm trying to say is it's something like this. Okay? If you do this, it gives you an inner product. Okay? That calculates a value. It's an inner product. Okay? So any matrix A that would satisfy this relationship is called the matrix representation of the inner product with respect to that basis. Okay? Now, another thing that we learned was that if you have a basis, so if basis B is ONB, what does ONB stand for?
Orthonormal basis.
Orthonormal basis, then the inner product, the matrix form of the inner product looks very simple. What is it? You end up with identity matrix, right? Yeah. Because, I mean, when we did this exercise for a few examples, we realized that the elements in this matrix A is really, so if you have basis vectors, say u1 through un, if these are basis, if this is the basis, then this matrix is really made of ui inner product uj. This gives you a number, right? So at the ith row and the jth column, you get this number. And if you fill this in for the entire matrix, that's how you get the matrix form of the inner product with respect to the given basis. But if it's an orthonormal basis, then we know that any two bases that have different I and j, they're orthogonal, which means the inner product is 0, right? And if you do ui with itself, ui, that's the norm of squared, but the normalized vectors have size 1, so 1 squared will be 1. So that's why only at the diagonal you're going to get 1, and you're going to get 0 everywhere else. And that's why you get this as the inner product, okay? So we did all this, but I guess I haven't spelled these out in a single complex format, so make sure that you know this, okay? And what I wanted to explain here is that if you have a matrix whose transpose is itself, it's called symmetric. Okay? It's symmetric. The two sides look the same. That's why it's called symmetric. But then you're going to see a counterpart if we use the Hermitian inner product. So now let's talk about the Hermitian inner product. Give me a moment, I need to choose the Now let's talk about the Hermitian inner product. What is a Hermitian inner product? Well, this time this is a Hermitian inner product on a complex vector space say complex vector space V, with basis again B. Right? Then, oh, maybe I haven't said here. Okay. Over here, if it's an orthonormal basis, this just becomes an identity matrix, right? So in that case, in this formula, the inner product doesn't require this A. This becomes identity. So this really says that inner product of UV, if these are both represented under this basis B, is just simply U transpose V. If you write down what these mean, so in R3, what's that? Like A1, A2, A3? will be a transpose of a column matrix. If you take A1, A2, A3, and you take the transpose, you get a row matrix. And you multiply with another vector, B1, B2, B3. How do you do the multiplication, matrix multiplication? It's across down, right? Then you end up with A1 times B1 plus A2 times B2 plus A3 times B3. What is that? That's the usual dot product that we know. Okay, so that's what I mean. If you have an orthonormal basis, then you have the regular dot product. Now, over here, when you have a complex vector space, you change just a little bit. What do you do? So when you have an orthonormal basis, then UV would be like U transpose V, but you do one more thing. Do you remember what that is?
Complex conjugate.
Yeah, you do a complex conjugate on the second one. Okay? And the reason you want to do this is so that if you have UU, you do get the correct meaning of the norm squared. In other words, this will always be positive unless U itself is 0. If it's 0, of course, the norm squared is 0. But every other case, you see that the norm squared will be positive. So that, in a sense, taking a complex conjugate here enables you to preserve this positive definiteness, okay, which is an important thing to do. Okay, so knowing this, now you kind of see that everything that we wrote here basically carries over. So if I say this with B, which is not necessarily orthonormal basis. If it's orthonormal basis, then this is what it's going to look like. But if it's not an orthonormal basis, again, you have some matrix. But then it should have the property that if you have U, A, U, bar, sorry. First of all, it should have the property that UV should equal to UA, V, U transpose. And notice that to be 100% correct, I have to put these betas there, but that only makes things complicated. So we're just going to assume that U and V are already matrices with respect to some basis, all right? So this, oh, I forgot the complex conjugate here. So that's what the Hermitian inner product is going to look like. And then if you look at this, U transpose A U bar is going to give you U transpose A U bar transpose U bar. Oh, okay. Yeah, all right. So let's think about the following. What is this then? This is U inner product with U, right? Then that's the norm squared. That's a real number. Okay? So it's a real number. It's a single number. If you take a conjugate of a single number, what do you get? A single real number, what do you get? If you take a conjugate, complex conjugate of a real number, it doesn't do anything because complex conjugate changes I to negative I, right? So it doesn't do anything. And also, because it's a one-by-one matrix, taking the transpose doesn't do anything either. But then if you actually do this, here's what you find. You see that this is going to be same as, well, first of all, transpose switches everything. So you have U bar transpose, A transpose, U transpose, transpose. So this goes here, and then you still have to do the complex conjugate. And then the complex conjugate can go down here and apply to individual ones, and transpose of transposes itself So what you end up with is this will be U transpose A transpose bar with U bar. Okay, because bar of bar is again itself. Okay? And from here, this being equal to this, and then then it takes a bit more work to show that this indeed says, if this is true for any vector u inside the entire vector space, then you can show that these two have to be the same. That takes a little bit more effort, but I'm going to skip that and just conclude, like hand waving a little bit here, and say that A transpose bar should be same as itself. Now notice that that's just a slight more addition to this condition, right? In fact, if you have any real symmetric matrix, taking the bar doesn't do anything, so this will always be true anyways, right? So we now have a name for this because this came from the Hermitian inner product. Any matrix satisfying such a thing will be called Hermitian. And in addition to this, there will be a counterpart with the positive definiteness, where the positive definiteness means that this quantity has to be positive. Yeah, but since my goal today is to talk about Hermitian rather than positive definiteness, let me just say this. Okay, so Hermitian matrices are matrices whose complex conjugate and then transpose is same as itself. Okay. Now you can sometimes you see this in the literature as taking the bar both sides and then bar of bar is canceled, so you end up with transpose of A is same as its complex conjugate. That's another way to say it. Okay. And in fact, that gives us a better idea of what a Hermitian matrix looks like. So an example of a Hermitian matrix would be something like this. First, the transpose doesn't do anything to the diagonal entries, right? Diagonal entries stay the same when you take the transpose. Transpose just flips over the diagonal, right? And because the diagonal has to equal to its complex conjugate, that means any Hermitian matrix must have real entries on the diagonal. So here's an example. If you have like 1 and then 2, that's good. These are real numbers. Right? On the other hand, the off-diagonal ones should say that something on the upper triangular region, when you take the transpose, should go to the other side, but with the conjugate. So let's say you have 1 plus I here, right? Then what should go in here? 1 minus I. Right? So that's an example. Now, any symmetric real matrices will be Hermitian matrix. I already said that, right? So if you have like 1, 1, 1, 2, that's still fine. That's a symmetric matrix, and it's all real. So this is a Hermitian matrix. So these are examples of Hermitian matrix.